and he's going to talk about constant pH MED simulation as a tool to unveil the pH effects on biomolecules.
Eu penso que isto está ao contrário. Nice. Can you hear me? So, good morning, everybody. The ones who resisted. So, my name is Miguel. I always have to spell for Portuguese, so I have to spell for everybody, right? Machuqueiro is really a strange name. But the good thing is that once you know it, you always remember it. So, I should start by thanking the organizers, really, and in particular to Vitor, because it was a really kind invitation to come here. And it's been just amazing 9 days. I actually sent a message to my family and my students that I might not coming back. No one replied though. So we just assumed that they are okay. And so what I bring you here today is a presentation on one of those subjects that is really annoying the community. It's like dealing with pH. It's one of those elephant or a mammoth in the room because people just try to push it under the rug, right? But nowadays there are a lot of methods to deal with this, and there is no reason why we should not take it into consideration. It would be just amazing to do like experimentalists. You just adjust pH, and unless you do something very bad to the simulation, pH tends to be buffered in specific value that you prefer. But once we go to simulation, we all know that this happens, right? You change pH and then the properties, the protonation stage change on the protein, everything changes. So that will affect the way the protein will interact and also will affect the way the protein will do its catalysis because, well, there are a lot of pH sensitive groups in active sites usually. And which residues are the culprits? So these are the pH sensitive residues, right? You all know this, I don't need to explain to you. This is the list of pKa's that is not taken from some old textbooks. This is actually pKa's measured on pentapeptides that were capped, and you just put the residues. These are alanine pentapeptides. You just put the X substituted by any of these groups, and then you have all these pKa's. This is amazing work by Nick Pace's lab, so we could use this data to calibrate most of the computational methods because we run calculations on the pentapeptides, and then we trace back to some model compounds that everybody needs to use in their models. But the thing is, we are measuring a pKa of a glutamic side chain in such a small peptide, and we all agree, okay, 425 seems reasonable, but the moment that we go into proteins, we know that that is not true. That's why there are so many people developing all of these methods to get all these pKa shifts, because that's what we want. We want to know if the pKa is upshifted, downshifted. That's what we want to catch. And you might start to have, like lysozyme has this glutamate that was like the holy grail. Everybody was trying to get the pKa of this. And when you do that based on a single structure, it becomes hard. And the experimental value is around 6.2, so it's an elevated pKa. And the reason is, we can look at it, and if your eyes are trained on electrostatics, you kind of know, okay, it's maybe just dissolvation. So the neutral form is a little bit overstabilized compared with the ionized form, and that makes the pKa shift a little bit. But the problem is that if we pick up any of the, maybe now hundreds, I didn't count them, structures for lysozyme, and if you run a calculation, you might run a QM calculation or a Boltzmann or a generalized Born Monte Carlo calculation on it, you get a pKa, but you'll have 100 pKa values. That is the problem, right? We all know that. And as if this was not already complicated, there was this guy in Lisbon that decided, no, let's look at the problem even at other interfaces. So imagine that you have a membrane, and now you have like, it can be a protein membrane or a peptide interact with the membrane. What happens to the 425 on this glutamate? It should shift, right? So it's interacting. It's like going inside into a protein. In this case, it's to a membrane. Technically, it's simpler, right? Membrane can be a little bit more homogeneous. And in our model, for sure, it's homogeneous. So because we are just doing a simple model with POPC. But imagine that we have our carboxylic acid. It's going to interact with choline groups, like the blue ones, and then with the phosphate group, you have the phosphorus here in what is that color? Like yellowish. And then you have the part where you have the tails. But when you reach the tails, the moment you don't have water, you don't have pH, technically you don't have pKa's. You'll have a proton binding affinity because it's a free energy. You can use a method to estimate it, but then it doesn't make any sense and it's not really useful. So what happens when we do this? We can actually, it's very difficult because there aren't many experimentalists measuring pKa's of pentapeptides in liposomes, for instance. It's difficult data to obtain. So what we decided was, okay, if we don't have anything to compare, and for sure, we'll not have a free energy, we'll not have a pKa, a computational pKa with all the information needed to compare with experimental, what we can do is we decide, okay, let's just calculate the pKa shift of the interaction. And that's a little bit easier. Not very easy, but it's easier. Because now you can use something like umbrella sampling. You can slice your membrane normal into small portions of space, and then you can calculate the pKa on here. Well, if it's too far away from the membrane, it will be 425. That we all agree on, right? But then when you start to come down, it will interact with choline charge, positively charged, phosphate, negatively charged, and then somehow we'll go through the whole desolvation process. So it's like a portfolio of what should happen to all the side chains of the amino acids in a membrane protein, because you'll have these groups in different portions of the membrane. And they don't stick to one region, they move around. So this is important to know. This is what we did quite some time ago. And the thing is, if you look at it, and you can follow, let's just follow the N-terminus. So indeed, N-terminus is a primary mean, and the shift is very important actually for what I'm showing after. So if you go to the N-terminus and you look at the pKa, you kind of have a little bit of like bump over here. It's the sampling is not really great, but it's enough for us to catch the interactions with cholines, the interaction with phosphate, because one will stabilize the neutral form, the other one will stabilize the protonated positively charged form. So you have all of these bumps in the profile because you are following it, and then you catch all the desolvation. And why is the desolvation so important? Because you can distinguish the cationic, they go left, stabilizing the neutral form, the anionic go right, they stabilize the neutral form also. But if you look at here, sometimes we don't have enough sampling because this was done some time ago, and the simulations, it's not a matter of forcing the group to go inside, because it goes, it's just that never ionizes. And then if it never ionizes during our simulations, we cannot calculate pKa's, right? You need always to do a ratio between the ionized and the neutral form to get pKa's. So how did we do these calculations? So this is the method that we can use. There are a lot of flavors nowadays of constant pH molecular dynamics. Most of you probably already know some of them. And the one that we developed in Lisbon is based on the Antonio Batista's work. And I learned this when I was a postdoc there, like 20 years ago. I'm getting old. And this method is rather simple. I can describe it in a nutshell. So imagine that you run a molecular dynamic simulation, you do a stop, you go to Poisson-Boltzmann, you get all the energies necessary to do the thermodynamic cycle. And then once you have these energies, you feed them to Monte Carlo, and the Monte Carlo will give you a representative step. And once you have that representative step, what you do is you go back to molecular dynamics and you change the protonation states. When you do that, because this is explicit solvent, you need to do this extra step, very short. You just need to allow the local water to rearrange, because this water was not expecting to have a proton there, and suddenly we just made one proton appear out of nowhere, so the water needs to rearrange. So this is why this is a hybrid method that requires this. So this method, I developed with Antonio the part for gromos, because we were like a gromos community there in Lisbon. But nowadays, I already extended it to charm and to amber, so we can actually run the same code to compare different force fields on the same project. For what can we use this? So we can use this for, let's see if this goes. Yeah, it goes. We can use this to estimate something quite nice, which is, this is like donepezil, so it has a pKa right 8.5, it's a Lewis base, and you can follow the protonation state of this donepezil once it goes inside the acetylcholinesterase. This is an acetylcholinesterase inhibitor. It's very, very known compound. And the funny thing is that if you run this calculation at pH 7.2, we assume that when it's far away, you see, this is distance. When it's very far, the difference between the pKa and the pH gives like 95%-ish of protonation. So if it's too far away, it doesn't feel the effect of the protein, so it should have like 95%. But then the funny thing is like this, look at it as an energy. So suddenly, it likes to be protonated, but then it goes into the channel, and then it doesn't like to be protonated anymore, but then it sees probably an anionic group over there. I think it's like an aspartate around here. So it feels, then goes again. So this is like an energy. It seems like it's a bumpy ride for it to go inside. But it also tells us that at pH 7, if there are some groups that can move to the side and can exchange protons with donepezil, give you a proton and then it goes faster. The protonation can be seen as the oil of the whole process, because it lowers the energy barriers of going through. But what this also tells us is that if you have 0.5% when you are in the X-ray position, it's a nightmare for docking, right? Imagine that you want to do docking. So what most people do is they run one of the cases. And to tell you something, it doesn't matter, because the docking scoring functions didn't take this into account. So it merged everything. And now we can go to the docking software, we change the protonation state, and we get almost the same energy. We know that that's not correct, but it's kind of, it was one for all. It was made to give a good result whether you do one way or the other. So it really does not capture the protonation effects. Technically, it's helping you, but then you start to think, whoa, if I really know that I should had one and this was not the correct one, probably I'm giving like 2 kcal per mole error right away, on top of those 2 kcal that I already had. But anyway, we also did something quite interesting with anti-tumor drugs. With this anti-tumor drug like sunitinib, it has also a tertiary amine over there. It's a Lewis base. And what we did was we just followed and studied the membrane permeation of the drug. We were interested in membrane permeation. We knew that it had this positive charge. And the trick is very simple. So you have the drug. The positive charge over here at pH 7 in water tells us that the drug is soluble. That's why most of these, like, antipsychotic drugs all have Lewis bases, because it's the only way they are soluble. They are so hydrophobic to cross the blood-brain barrier that it's inevitable. Then someone very smart back then just decided to, okay, let's add some solubility, otherwise we'll not have a pill, and everybody needs to take a pill, right? So the problem here, and that's what I'm going to try to convince, is that the same strategy were used for anti-tumor drugs, and the drug goes from here to here. When it's in the center of the membrane, deprotonates. It's a transient deprotonation. The process is very well known. And it's required because you don't see a cationic group like this crossing a membrane. The energy barrier is just too high. So for passive diffusion, you actually need to deprotonate to do it. The consequence is this. If you need to deprotonate, you are a pH-dependent process. So it means that if you find some acidic tumor, you will have a hard time deprotonating, because it's much harder to deprotonate when you are at lower pH. And that's why also in lysosomes there's this called the lysosomal sequestration. Most of these drugs, when they fall into a lysosome, it's like a black hole. They just they are not able to get out because they cannot deprotonate, and they get trapped inside lysosomes. That's why tumor cells overexpress lysosomes, which is another way of creating anti-tumor drugs resistance. But this factor of 10 that you see here, this is annoying, right? This means that we have to take 10 times more of those to actually reach the tumor. and with all the side effects. So this is, it doesn't happen with all the drugs, but some of them, I think that we should be a little bit smarter when designing some of these drugs, at least take in consideration these pH effects. The work I wanted to show you, and I have 5 minutes for that. Well, I can steal a couple of minutes afterwards for my discussion because you will not have questions. So, so if you look at this, these are, I think all of you already heard about dendrimers. PAMAM is very known, but there are a lot of these dendrimers around. But probably many of you don't know is that you can build dendrimers out of amino acids. So you can make peptides. Instead of a peptide doing a polypeptidic chain, you just start to branch them. And then you start to have dendritic peptides. Why are these so interesting? So experimentalists decided to, okay, we can do catalysis, we can do a lot of process, we can mimic enzymes, even without secondary structure, because most of these molecules, they are too flexible, they don't have secondary structure. So Tamis was my PhD supervisor when I was in Bern. And then many years after, she was developing all of this stuff, and he asked us to do the models. And she was very interested in these specific sequences because they were quite good for transfection. They are highly positive. I can show you on another slide the structure. So they are just built of lysines and leucines. They keep it simple. It's like it's not a round cow, but it's quite a simple because it's too complicated. And there are some of these dendrimers that were created out of shuffling from direct evolution methods, but here they were just designing them by hand. So and you can see there's these green lysines. That's because the side chain of the lysine is used to propagate. For this to work, of course, you have to build from the C to the N termini, right? It's a little bit, sometimes it makes a little bit confusion, but if you think of this as the C termini, there are like a lot of N termini on this side. And we have these two families because we decided to remove just 4 lysines on the 47 dendrimer. The rest, everything is the same. It just has 4 less lysines. And these molecules, it has this, if you want to know what is the charge, you look at it, it has an N-terminus over here, and it has a side chain of a lysine. You know the pKa in water, they will be mostly water exposed, most of these residues, so the pKa should not shift due to dissolvation. But as a battery, once you start putting protons, we start to see some effects on that because it's easy to, on your cell phone, it's easy to charge until 80%, but after that, it starts to get crowded and it's difficult to add electrons. In this case, it's difficult to add protons. And these molecules are highly flexible and they also can kill graphic cards, it seems. But the only way that we can characterize this is really this is polymer chemistry. It's like radius of gyration. It's the best way to capture what is going on. Sometimes they compact, sometimes they expand. And this is what we knew from experiments. We knew that some of these families were quite good at doing some things, were not so good doing others, and the experimenters didn't know what was the reason. So for transfection, you actually need to bind, in this case like siRNA. So you need to bind siRNA. That is okay. And they knew that they were both very good because they both had charge. They had this hydrophobic character. So they had all the characteristics to bind nucleic acid. So that was good. And then they should adhere to the membrane quite fast so that they could start and create an endosome. And this, actually, the most hydrophobic one is better. It's also not surprising, I would say. But then the real gene silencing part, so the part where it gets out of the endosome when it's acidified, that part, you could actually see a difference. And this is why they were so puzzled. Why are those 4 lysines that important for this process? If so, it means that the other one that works better might be at the limit, and we could improve it. So, but they wanted to have our take on that. And then we look at full titration curves. We use our Constant-pH molecular dynamics. We look at it and we say, okay, this is lysine titrating. For sure, on the side, there will be the N-termini. But you see, you need to go to pH 5 or even 4 to actually fill all the sides of the N-termini to protonate, because it's hard. The amount of charge emanated is very high. And you can decompose this by generations, because there will be the lysines on the center and then the lysines on the shell. And of course, the radius of gyration will depend on the charge. And there are a lot of variations, but let's concentrate just on the two that I showed you, because these are like using the amino acids instead of L, because they had all of these experimental data and we wanted to compare. And the thing is, we don't have much sampling, but we had enough something to see that, okay, if you don't have so much positive charge accumulated, then you can compact more. So it's an electrostatic driven process of expanding and contracting, and we coded that. But then we did the simulations with the membrane, and once we run the simulations, the first thing that you notice is that these are like octopus. They just, all the positive charge start to look for the next available phosphate. That's what they do. And they do all these interactions, but they are not locked. So they are always exchanging, because there are so many phosphates, so many charges. So this is the process that we see. And so at pH 7, this is what we see. And once we calculated the position in terms of the average of the phosphates, so if you calculate the position of how the phosphates are dragged by the presence, we kind of can get the profile of deformation. That's what we are trying to do here. I think, yeah. So imagine, at pH 7, there's almost no deformation. That's what you see here. So when you sit a protein or a peptide dendrimer on top of a membrane, of course the phosphates will go slightly inside. They are dragged a little bit, but not too much. But the thing is, you see it already here. Once you go into more acidic pH, then we start to see a large deformation, and this is a typical conformation. So this is like the beginning of something that we think that might be like a local deformation, maybe even creating pores and this kind of mechanism that we know that sometimes this can happen from antimicrobial peptides and all these cationic molecules that are allowed to do this. And the funny part is that those 4 lysines were enough for the second dendrimer not to do the same process. And even at pH 4, it doesn't change the membrane as much. And this, we could see this in most of the replicates. On average, we really see a clear difference. So those 4 lysines were enough to make the difference. But then this is a more complicated plot, and I don't have much time. But the idea is, if we follow the protonation on 18 or 47, and this is the protonation of the protonation of the lysine is not so important, but on the N-termini, you see these are the ones that need to charge once you go from pH 7 to 4.5, right? These are the ones that are going to make the trick. And the profiles are exactly the same. So it seems like the N-termini doesn't know that there are 4 lysines missing. It's kind of the profile, it will behave the same way. So it seems like it's just the amount of charge. That's the take-home message. It's just the charge density, the amount of charge that you are able to generate in this kind of spike, this hole that you make in the membrane. You need to have a lot of charge there to actually start to make a dent into the membrane. If you don't have this much charge, you will not have it. And this is just a slide to show you what we are doing now. I added these slides last minute just to show you that what we are doing. We are doing the interaction with the siRNA. These are nice simulations. But we are only at this point of launching like dozens of simulations just to see the docking. Because it's very difficult to have a good sampling on this process with such atomistic models, right? Imagine, you drop 10 times, it will dock 10 different ways. And then, well, we can average that, but you kind of are not doing averages of stuff that you should be doing. So this is the group. I have to thank the people. Most of this work of the dendrimers is the work of Phil over here. And everybody does their own thing, because the glue that glues everybody is actually this pH dependence and developing of methods. People are expanding to different force fields, different codes. So that's why it's a big mess. So you have people working on membrane proteins and others working on, well, peptide dendrimers, for instance. And let me shamelessly advertise protein electrostatics next year. So this is a meeting that happens in Telluride. Some of you know this protein electrostatics meeting. And every 2 years, we do it in Europe. So next year, we'll do it in Lisbon. And we are still updating the website, but take a look at it and maybe you are interested and come and visit. You don't need much of a reason to come to Lisbon, but this is half of a reason to come to Lisbon. So, and thank you all for the presentation.
Thank you, Miguel, for a very wonderful talk. And questions?
Hi, Miguel. Thank you for the talk. This one is actually a comment and a question.
Sure.
So with Vitor, we basically implemented the Batista method for the structure-based model, so we could sample either the unfolded state, transition state, and the folded state. And many of the shifts, when people compute, use the computer actually methods to compare with the experiments, the deviations comes because they do not actually include many of the unfolded structure that you may have in the experiments. And then my question is, if you could comment on that, when you go to extremes pH, how much you deviate the structure that you have in the experiment, how much you can accommodate this when going towards your method. And then the second question would be, how about the time scales? How often do you actually test the protonation, and if you have some experiments to compare with?
Mm-hmm. Two very nice questions. The second one is really deep, but let's go on the first one. Yeah, once you get out, this only works if the force field is good. That's the take-home message. Now that we compare between force fields, I see all the holes. Of course, I see a small part because this is my backyard. That's where, when I play around here, I see the holes. Of course, other people see other holes, but I can see them. Imagine, carboxylic acids, when they are neutral, the parameters in many force fields, they were not as good, but over the years they got much better. So now if you want to protonate a glutamic acid, the parameters are really quite reasonable. And we always have good predictions for carboxylic acids. But an example of that, if you go to high pH, the deviation starts to occur much stronger. And this is in our paper where we did the charm 36M. So because things get stickier, and imagine you have a Poisson-Boltzmann method that realizes that the exchange between the bound and unbound needs to occur, because otherwise you are shifting the ensemble, the conformational ensemble, and then your pK predictions are quite bad. So in principle, we could get better predictions of pKa's even than experimentalists, because we don't have limitations that experimentalist has, because things start to unfold and very bad things start to happen, unless you use like peptides or something. But in fact, we don't, our predictions. And so your question makes a lot of sense. Regarding time scale, that it depends on the force field. There are force fields that are just incredible fluid. I heard, I think, in previous presentation, people talking about some coarse-grained force field because everything is very, very fluid. There's a difference between Gromos and Amber and Charm. And the reason is Gromos is much more fluid. Incredibly more fluid. I can see a lot of stuff happening in Gromos that it would take an order of magnitude of simulation time to see it. Of course, if you see a lot of stuff, you start to see a lot of more problems earlier. And that is like the problem with Gromos. But the time scale on that point depends on the force field. And now second. Yeah, exactly. That was my second address. So for the second address has to do with the proton availability. This a lot of people raising, even like in August in ACS meeting. This was a big discussion. And it has to do with the proton kinetics, exactly as Jose mentioned. Yeah, that is a real problem. In our method, no, we don't care of that, because we try every 20 picoseconds to ask a group, do you like a proton? And the proton will come out of nowhere. So we don't have that problem. But protonation kinetics depends on pH. So imagine at pH 2, probably it's very similar to what I'm doing. But at pH 10, it's really a nightmare.
Right, but you can say that you don't care. But in practice, you have to care, because the proton has to get there, and the proton may be moving at the same time, right? So in your case, you're just bringing it from nowhere. So you may have a time scale problem here in terms of
Agreed. So it means that all my kinetic properties will be affected. Agreed.
So you're telling me that if you have to equilibrium, you can say it's only magnetic properties.
Yeah.
But the system is not able to equilibrate. That is deeper than that.
But there's no reason why it shouldn't equilibrate.
I don't know what's the time scale that since they're moving compared to have enough protons coming in and out.
But if the time scale is too large that you would have a problem to reach there, you have a problem either way. There's no, you cannot escape. It means that you chose the wrong project to work on, or the wrong methodology to work on.
I have had this argument with Charlie Brooks for a long time. I haven't agreed on that yet.
You haven't agreed, yeah, okay.
Okay. Other questions? There.
But it is a good argument. I like this argument. I have also had this with Yana Shen.
Hi, Miguel.
Yep.
Nice talk. I'm glad to see Poisson-Boltzmann screen. My point is, in your simulation, every step you need to go to the, let's say, Delphi and solve the Poisson-Boltzmann equation.
Yep.
Okay. So if we come with a kind of a spherical Cal solution, and let's say if you don't need to look at the full structure of your pentapeptide, if you can keep track of this charge, a point charge, can you do that? Can we skip the details and keep track only of this translocation of the point charge?
And get an analytic solution.
Because there is an analytical solution for that. We
Yeah, I
have
know.
this still model that allows
I haven't
for that.
seen one that works here. I've seen a lot of people promising, and Walter Rocchio, when he does this meeting, he likes to invite a lot of people from mathematics to come and give opinions. We always have a lot of people saying, it should be rather easy. That's the expression.
No,
but I haven't seen.
No, this is not easy because only recently we saw closed form solutions for that problem.
Really?
Yes.
Okay,
recently.
then it should not be easy.
I have another. Do I have time for another comment on that?
Yep.
Usually in the past, when people talk about these shifts in pK, they try to justify in terms of the changes in the local dielectric constant. So changing the epsilon, you get change in pK. Can you reverse gears and based on your pK shifts, we get some epsilon as a function of x? Could you do that?
You could. It's just there's no carrot in doing that.
Okay.
The idea of changing or adjusting the dielectric constant comes because you don't have. It comes, and it's very important for methods where there's no flexibility. So if Emil Alexov does that, and he does that because he wants to predict all the pKa's of the PDB data bank from rigid structures, and he wants to see the pKa's converging when you use different crystal structures. That would be. I think it's utopian. In my method, I don't have that because I use dielectric constant of 2. I would like to use 1, but it's not polarizable, so I use 2. And the dielectric constant is a non-issue in my simulations. But it's true. If you would like to pick up my trajectories and fit to experimental data, you could actually have a map with the dielectric constant over time. Yeah.
Well, thank you.
There's another question here.
Hi, Miguel. It's always nice to see electrostatic treats Lee very nicely. I was wondering if you ever had a chance to check the dependence of your pKa shifts with the extent of your environment around that probe site and how much the pKa shifts depend on the size of your environment, if you know what I mean. Because you mentioned that in
The electrostatic embedding.
basically that, the size of your embedding. Because you mentioned that in some of your lysines, you get it very hard to protonate as you protonate further, but they are very far away in some cases.
Uh-huh.
So I was wondering if you ever had the chance to check that because it's quite far.
Yeah, we can calculate the electrostatic potential. We can make a grid. This comes from Poisson-Boltzmann. So imagine you put a grid and you calculate the electrostatic potential on top of all those nodes. So you can actually see the waves of the electrostatic generated. And this is usually what is done in a method to catch the background effect. Then there are interactions. So a group interacts with another group that's calculated separately. That's the thermodynamic cycle formalism of this method goes like that. But yes, it's very important. And it's so important, that's exactly what we did when we did the AI method to predict pKa's. So what we did was we threw away everything and you just use the We even threw away carbon. So we just use oxygen and nitrogen and sulfur, the position of these atoms, and this gives the embedding good enough to actually predict pKa's. And we did it because we wanted something very fast. Probably we could have done better if we used other atoms or other features of the structure. But yeah, our pKai method that we have that is very instantaneous uses exactly the embedding, electrostatic embedding to infer on pKa's. And it was not trained on the experimental pKa's values. A lot of methods do that, but there aren't enough. And if you know about them, many of them are erroneous. They are like pKa's of cysteines are completely wrong on the database. But we train it on the pKi. So we train on the computer pKa's, which upset a lot of people.
So,
Questions? Do you have a
yeah,
question?
we are. So last question, and probably on behalf of Teresa, she was not able to come, but probably she will ask, could you comment on how all these changes modulate the membrane themselves, how it's coupled with all the deformations that you expect to occur, particularly when we look at peptides and stuff like that?
It's a little bit force field dependent because it seems like every single force field, I don't know if you guys know this, but every single force field, they keep membranes fluid with a different strategy. Some of them are similar, but are not the same, which means that a peptide can induce a slightly different perturbation in the membrane. So charges will have a large impact on Gromos membranes, but not so large impact on charm. I don't know which one is correct. Probably none of them. But anyway, but you have that. But I think the next step will be, how about lipids? Will they change protonation? Sure they will. The moment that you start to have more than 10-15% of anionic lipids, which most eukaryotic membranes have, you'll know those lipids should not be all of them charged because the effect is similar to what I showed you with the lysines. They accumulate charge, but it's hard to protonate. So now imagine go from the 3D world to the 2D world, something that I heard this morning with Peter. He was describing that. When you go from the 3D world to the 2D world, and the fact that the lipids are packed, the repulsion, the phosphate repulsion is much higher. So the pKa of phosphatidylserine or phosphatidylglycerol, which should be around 3, it's actually, if you start to add 5-10%, the pKa's will start to go 5, 6, and suddenly they will start to protonate and do all those amazing things like proton skating over the surface, the stuff that we need for bioenergetics, to produce energy. This all comes from these anionic membranes.
Great. Any other questions? Then I think you make a break right now and we come back at 11. Now it's the coffee.
Yes, and before